So now we are come to it. We are now ready to construct a principled statistical test of the bona fides of Bert's IQ data. What is the key principle? We've seen this before. The idea is to compare the actual data with the results of a Gedanken probability experiment, a thought experiment, and ask, are the data representative of that experiment? Are they aberrant with respect to that conceived thought experiment? We've seen this before in the analysis of the hot hand phenomenon. We've seen this in drug testing. We've seen this in the context of polls. It's the same idea for a principled statistical test. So we are going to compare Bert's reported IQ data for adults and children with what one would obtain, this is the thought experiment, from a random sample generated from a normal distribution centered at 100 with a spread of 15 or a variance of 225. To remind you of the setting, here is this projected random sample, a sample of size n drawn from the distribution, with the sample put into 8 IQ bins, and the number of elements in each IQ bin will then be binomially distributed with parameters n and a coin bias probability p, which depends upon the bin, p1, p2, p3 to p8. Okay, now we are armed. We now know the principle. We know the underlying statistics and the probability distributions, and now all that remains is the execution. Well, there's still a step to be made. What is our key observation again? Remember that each of the values Sn1 through Sn8, a generic value Snk for bin k, will take values via the law of large numbers near the expectation n times p of k. And if we view this properly by centering and in the proper scale, then these values S and k will behave normally like a bell curve around the expectation. This is the key idea. And so, what is our statistical test? Well, we want to compare the values S and k with n times pk. What should such a test do? Well, if we only have one bin, it is easy. This is exactly the context of polls. We know exactly how to do this test. But now we have 8 bins. How do we read this riddle? What do we do now? Do we do them one at a time for each of the bins? That is surely possible. But we're going to run into a difficulty, a subtle difficulty here. And that is, bear in mind that every time we do an estimation, we incur a statistical error and have to suffer a certain confidence. The confidence, albeit, could be high, say 95% or 99%. But when you do multiple tests, each of them at a relatively high confidence, collectively the confidence leaks, and we have much lower confidence in the whole. At least one of them might turn out to be bad. So doing them one at a time is the reasonable thing to try to do, but has a subtle reason running against it. So we need a new test. I'm going to go back to 2 maxims suggested by T.W. Körner, which seem very appropriate for this setting. First, whatever the test we develop, it should be easy to apply. Computational complexity reduction is a desideratum sorely to be wished. We are following along with the dictates of William of Ockham. You remember, the 13th century Franciscan philosopher and monk, who opined that we should find simple explanations for data, or whenever possible, eschew complexity if it were not needed. Of course, we recognize that this is the cornerstone of all modern science. So, we want a computationally simple test. And 2, we want the test to be fair. It should fairly treat all the data in fair and just proportion. So thus, for example, a test which only tests the last IQ bin and ignores the others, would be unfair. It weights everything down to one component. We want to check all the IQ bins fairly and evenly.